Welcome to Talk Universe. I'm your host, Sir Charles Schultz, and this is our show for Wednesday, December 21st, 2016. Tonight's show is all about navigation, its history, where it comes from, how we do it. We're going to cover a lot of the different aspects of finding our way around the world and in the universe, and how we pull it off. A lot of times we simply go somewhere using landmarks to navigate by or figure out where we are. And yet there's a lot more to it than that. If you think about it, even something as tiny as a gnat or a fruit fly can figure out how to get around. With a brain with just a few tens or hundreds of thousands of neurons, how in the world can they do it? We have some very sophisticated systems today that allow us to navigate by the stars, by maps of pulsars in deep space, by GPS satellites, and any other number of means that you can think of. So let's have a look at that in detail, see what it's all about. It's really fascinating stuff. We're also going to be joined by Ed Minchow, my co-host, who has done a great deal of research and has a lot of expertise in the field, and we're going to share some interesting historical and technical perspectives on navigation. But we also have a few questions left over from last week where a number of people really enjoyed the show and sent in some more questions. So we're going to cover a couple of those very quickly here. Kuresh from Pakistan says, what is the Curie temperature? This is a really interesting subject. Everybody who knows anything about physics knows that Madame Curie, who is a two-time Nobel Prize winner, became famous for the work done with her husband and being the first people to extract a natural source of radioactivity, radium, the element radium. And yes, she won 2 Nobel Prizes for the research she did. But her name was carried on in this effect. The temperature of materials when they are heated can affect how they operate. In this case, the Curie temperature is the point where the magnetism of a material vanishes. Imagine having a piece of steel, and it's attracted to a magnet, and you heat the steel up, and at some point, there's a transition that occurs so that the steel will no longer be attracted by the magnet. Well, many different alloys are made that have a wide range of temperatures at which they do this switching effect. We can control where it happens. And it's often used to act as a switch for controlling the temperature of something like a soldering iron. Anyone who uses the Weller temperature-controlled soldering irons, they know they have a tip that you put in that has a number stamped in the base, and it's a temperature in hundreds of degrees Fahrenheit. So you can put a 6 tip in it, and it will switch on and off and keep itself at 600 degrees Fahrenheit. And it does it because when the material is heated, the atoms in it are attracted to a magnetic field at normal temperatures, but the more they oscillate, the more they vibrate around due to temperature, due to thermal effects, the less able they are to hold a magnetic field until it collapses. And so then they lose their magnetism, and the switch that keeps the heater on turns off. Now, this is a reversible effect. So as soon as the material cools, it regains its magnetism and is able to be attracted again. So Curie temperature is the point at which ferromagnetism, the ability to be attracted by a magnet, vanishes. Scott from Florida asks, he says, my interest is in energy independence. How can we achieve that in the best way in these times? And he also says, how can a homeowner best become energy independent? Well, Scott, that's a great email, and thank you. And I'd say this. Now, it may seem a little strange, but the 2 largest obstacles are regulation and storage systems. And a lot of communities have laws and regulations that prevent homeowners from becoming independent of the grid, or they tax the use of the system so that it becomes too expensive to use. And so this is our real problem. Now, because the storage technology is also an issue, and it's because of the cost of battery systems, that's also one of our biggest issues. Batteries have limited lifespans and they're expensive, and generating the power isn't difficult, but storing it is the problem. So when you put the cost of batteries, charging systems, and inverters together, that's typically half or more of the cost of your system. But the best strategy is when you have more than one generating method. So if you had solar panels for daytime power collection and maybe a wind system to back that up, then you can gain power from either or both systems whenever it's present, because you can't get solar power at night, but you could get wind, and you can get wind during the day or whenever it blows. So 2 systems are better than one, certainly. 2 sources are better than one. And by the way, a lot of people talk about hydrogen as generating power, but it's really a storage system. And the problem is hydrogen is so fluffy, so lightweight, that it takes a huge volume in order to store any of it to give you any capacity. So the other thing is a lot of people generate power from solar or whatever and use the excess to make hydrogen. Well, this is okay, but the problem is you're only going to get about 20% of that power back, because that's what the losses are in generating hydrogen. So it would be a lot better to go to a chemical storage system if you're doing this sort of storage. Methanol can be made using artificial photosynthesis or synthetic photosynthesis, and methanol can be stored in a glass bottle or a metal can for an indefinite period of time. They have sunlight-catalyzed devices that take CO2 out of the air. Let me back that up a little. It doesn't have to be just out of the air. They can take CO2 in water solution as well and convert it to a 50-50 mixture of water and methanol. And what's great about this is that there are a number of fuel cells that run on methanol water, and that way you have the ability to use an existing off-the-shelf power cell, a fuel cell, that'll burn the methanol you make. So you could store that. You could just keep building it up as much as you want, because a glass bottle or a big metal can store hours or days or weeks of fuel to run your fuel cell on. Now, if we can get the graphene capacitors, the storage systems, into production, I would expect that we could bring the cost of alternative energy in half. And so the other thing is, if you have a hot water system, water heaters should be super insulated because they're losing heat all the time. They're usually pretty poorly insulated. If you'll notice, you turn them off and an hour later there's no hot water. That's a very poor situation. And if you're making hot water, don't do it with photovoltaic. Use it with direct heat capture. The flat panel solar heating system is the very best. It has an efficiency as high as 50%, whereas photovoltaic is generally only about 20%. And that's one of the things you got to keep in mind. It doesn't matter how you generate power. If you have a good storage system that's efficient and doesn't cost a lot, you can generate power any way you want, and as long as you can store it, you're in good shape. So you don't have to have anything immense, roof covering or yard covering. It can be something small that takes a little bit of power over a long period of time and saves it up for you. For our Singularity news, for the first time we've seen the light from antimatter. At CERN, there is an alpha collaboration project which has been running for over 20 years, and the idea was to create antiprotons and anti-electrons, put them together and make antimatter hydrogen. This has finally been done, and in each shot they capture approximately 14 atoms of antihydrogen in their trap. When they illuminated them with a laser, they caused something called the 1s to 2s transition, which creates a spectral fingerprint of light from the atoms of antimatter. And what they discovered is they are absolutely identical to normal hydrogen, which means they follow the exact same laws of physics, which is what they predicted. Jeffrey Hanks, who's a spokesperson for the Alpha collaboration, said they were using a laser to observe a transition in antihydrogen and comparing it to normal hydrogen to see if they obey the same laws of physics. And that's always been a key goal for antimatter research. So it was successful. They have made antimatter hydrogen, and it is absolutely identical optically as predicted to normal hydrogen. This is a key step forward in understanding antimatter physics. Mars may have harbored life for hundreds of millions of years. Curiosity rover science team member John Grotzinger says that the conditions for life could have been present for many millions of years, and that the area of Gale Crater, which is where the Curiosity rover is presently located, has dried and refilled with water many times in the past. He spoke to the American Geophysical Union and presented the information, stating that Gale Crater was most likely host to a vast lake and stream system, but water was not present continuously. He also said that doesn't necessarily mean everything living there disappeared with the water, though. He also went on to say that the presence of organisms would also be affected by the presence of the water table, among other factors. Would you like a bionic accessory that helps you have better memory? Theodore Berger, the biomedical engineer at the University of Southern California, is designing a memory prosthesis. This is a device which would be implanted in the brain surgically and act like the hippocampus area of the brain by electrically stimulating the brain to encourage the formation of memories. By studying the way that associated memories are formed through experience, he's learned some of the rules that convert short-term memories into long-term memories. Presently, human trials are being conducted. Now, what the hippocampus does is a part of the brain that is basically right in the center of the brain, and it associates memories, both short-term and long-term, different experiences, and effectively creates something like an index card that ties different parts of your sensory system together so that the look or feel or touch of something will be tied up with the experiences. It allows you to associate sensory data and other memories and create sort of an index card, so it's easy to find it as a whole memory. What this device does is acts like the hippocampus and creates the signals that tell the brain how to make that little index card that ties the whole memory together. And that's our Singularity Watch for this week. So there's no question that memory plays a big part in our ability to navigate, and it does so for many organisms. Anything can recognize a marker and then go back to it and use it as a reference point. Well, navigation began this way in most organisms, the ability to recognize a marker or some sort of a location and use it as a base point. We can see some things, even as simple as cells or tiny organisms, can do this. We certainly, like I mentioned earlier, can see that gnats and flies have the ability to recognize locations and go back. And there's no question we see bees and wasps have to be able to do it because they would never be able to find their nest otherwise. So ask yourself, how does something that tiny with so little memory, a brain smaller than a pinhead, figure out where in the world it is and how to get back to it? It turns out it's really not that difficult. Let's take the case of ants. Ants are often looking for food, places to dig, or what other resources they need, and they do it after they've moved around by leaving a scent trail. Other ants can follow that scent trail very easily and find their way to the nest or to whatever the target is. This is really no different from us navigating through the woods and leaving a trail of bent twigs to show us where we're supposed to be going, or even putting signposts out. So signpost navigation is a pretty simple one. You don't even have to know where the track goes, you simply have to look for the next signpost. That's probably one of the simplest ways of navigating that there is. You don't have to remember anything. This is also something that a lot of us do unconsciously. We travel around, we look at our landmarks, and we take them as signposts. Landmark navigation is a little more complex than a signpost navigation. Signpost, you typically have one identical signal that you look for over and over, like a scent or a color or a sign or a marker. With landmark navigation, it becomes more complex because you have to remember a number of landmarks, and you may see them from different angles, so the complexity grows a bit. But this isn't even a difficult one to solve because of the way our brains work. We memorize the aspects of an object or something that is outstanding, and we make a model of it in our heads so we can imagine it from a number of different angles. Now, we've all been in a neighborhood where we were looking for something and we pick a mark such as a water tower or a radio tower or a tall steeple, and we use it to help us get around in a neighborhood. We're doing exactly that. This isn't signpost navigation, but landmark navigation. Bees, wasps, and hornets, mud daubers, all of them take advantage of this sort of navigation as well. But they do it in a very curious way, and if you'll ever watch a bee or a wasp or a mud dauber trying to establish a new location, it will fly in and it will scan the area and fly away, and then it'll come back and it'll do it again and it'll do it again. And it will do this at least 3 times because it's fixing the memory in its little mind. So it's actually taking the elements that it sees and almost making a snapshot of a sort. It's getting a model of the objects and making a snapshot of their functions or their structures in its mind. And then it's making a second memory that lays them out in a specific order. This is the most important part. You may know 3 landmarks, such as a flashlight, a tree, and a red sign, but if they're not in the proper order or in the proper relation to each other, you're not in the right place. So we have 2 levels of memory involved in landmark navigation. One is to know the actual landmarks themselves, and the other is to know what order they have to be in for us to be in the right location. So you see, it's not a simple photograph of the area sort of thing. So this is a really simple introduction to signpost navigation and landmark navigation, but there are other types as well. When we got into technical methods, we found that timing and the angle of the stars could be used to tell us where we were. And the invention of the chronograph, the very accurate clock that could be carried from one location to another, was a huge advancement in marine navigation, and the positions of the stars, which is something that had been studied for many thousands of years and noted very accurately, allowed us to combine both time and the positions of the stars to show us where we would be navigating in a ship by latitude and longitude. So time becomes an important part, and the use of the compass, the discovery of the Lodestone, magnetically aimed to the north of the planet, and its alignment with Polaris, the North Star, all of these things came together to create a larger sort of navigation that doesn't depend on the landmarks on the Earth, but instead depends on the movement of the sky and time, and the location of the fact that there is a magnetic field around the planet. So when we start looking at gyroscopes and inertial navigation and the constellation of GPS satellites, we see that there's a lot more to this than it seems. And we now live in an age where computing becomes our major method of getting around. So let's look at that after the break. This is Talk Universe. I'm Sir Charles Schultz. Imagine floating in space in the darkness between the planets. Space isn't a place where you can leave a mark. The vacuum is frictionless, unmarked, and unmarkable. Everything in space is falling all the time, and no marker, no road mark, no landmark can stay anywhere you put it. How do you know where you are? How do you know how fast you're moving? You don't have any references. On the Earth, it's easy. You see the ground, you see the sky, you see the landmarks. But in the vacuum, in the nothingness, how do you know just where you are and where you're going? That can be a real problem. Early rockets were really insensible things. They didn't have computing technology, and the only way they could get around was with inertial methods. Gyroscopes were used. Scientists and engineers would create small spinning devices that have one upright axis and suspend them in gimbals so they could freely move around with response to their environment. Rockets carrying a gyroscope could definitely know which of its three axes, X, Y, and Z, were pointed in which direction, and would use this information electronically to plot where it had moved. Furthermore, with the information of acceleration, the change of velocity that they had, they could mathematically calculate the path that they would be on. But long before the gyroscope and long before inertial navigation, there were some things that existed in nature that men learned to take advantage of, and one was a special type of stone made of a material called magnetite, an iron oxide form. This material naturally is magnetized by the Earth's field and is called lodestone. Now, lodestone is a very interesting mineral and responds by pointing in one direction. It was actually considered magic by many and was one of those rare materials that, when discovered, became essential to navigation. Having a compass, something that actually pointed in the same direction all the time, was something that was just about mystical in those days. And if you really think about it, it takes a bit of thinking to realize that most of the navigational challenges were not on the land, but they were at sea. Because when you're at sea, usually there are no landmarks. You're again basically in an endless void. And so having a compass is an excellent help because you can pick a direction, and using the compass you can aim in that direction. But the other half of the equation, besides arriving at your destination, is knowing how far you've gone. So how do you measure your speed? It becomes pretty obvious that you need some sort of speedometer. And the speedometer in this case was a board with a long rope with knots in it at uniform intervals. And it would be dumped overboard, and you would measure how much rope fed out in a unit of time. And in that period of time, you would count the number of knots that slipped through your hands, and that was your speed in knots. Now you have your compass, you have your speedometer measuring your speed in knots, and you have a good idea of the direction and how fast you're going. If you knew how long you traveled, with a good clock to do your timing, then you could get an accurate assessment of just how much distance you had covered in a unit of time. And ships' chronometers were very, very exclusive devices, extremely accurate, and carefully guarded by the captain. Now, there's only one other thing that stands out here. You need a map. Unless you know where you're going, all of this information is useless. And so maps were the most prized possessions of any navigator, because you could always find a way to navigate, whether by the sun or by the stars or by the moon. But unless you had a map to start with, you really had no idea where you were going to go. And I don't think it would be lost on any of the listeners to realize that the word navigate and navy all start with the same three letters. This is because they share the same common word. Navigation literally meant to get around on the seas, or more correctly, to travel in a ship. Now, navis, the Latin word, means ship, and agere means to drive, and navigas, or navigate, meant to sail or move in a ship. So that's the root of the word. But in recent times has come to mean figuring out how to get around from one place to another successfully. What's really amazing to some people is that recently a 2,000-year-old Greek ship was recovered, and when they found it, there was an encrusted bit of coral and metal found in the bottom. Well, when they tried to clean it, they were worried about damaging it, and it remained in a museum for quite a while, but X-rays showed that it contained a complex mechanism of gears made of brass. Later, when it was given a great thorough analysis and a reconstructed model was created, it was discovered that this device was actually some sort of mechanical computer. But it showed an interesting gear ratio of 19.5 to 1. What's significant about this is it proves to be the foundation of a navigating machine that predicts successfully the positions of the stars and the planets. It can be set to a given date and then run ahead or behind to predict where they will appear in the sky. This is actually an ancient navigation computer called the Antikythera. And what it's showing us is that there was some advanced technology even in Greek times. You see, these machines were mass-produced on a small scale and outfitted in many of their ships as a standard bit of navigational hardware. This device is truly a computer and is programmable. And it shows you that they had the ability to produce flat brass stock in a uniform way, and they must have had the facility for cutting gears like a machine shop successfully, repetitively. So it means to us that there is some lost technology, something forgotten or not shown in our history, and this is one of those unusual devices that turns up from time to time that shows the sophistication of some of our forebears, particularly in the arts of navigation. But of course it becomes clear that navigating also relied on the map, as stated earlier, and map-making and cartography as a whole gained its skills at the same time we were figuring out how to navigate. After all, if you didn't have a chart telling you where to go, you wouldn't know which direction to start. So the development of cartography, map-making, and navigation actually went hand in hand because of this. Now, surveying is basically the angle measurements, distance measurements, and other things that you can use to create the points on a map, which can accurately record the structures and distances and shapes of plots of land. When you combine surveying and navigation, you find that the two work with each other to produce the best results. Of course, early surveying was pretty much laying rods of known length on the ground along a straight line and then measuring them. But as optics improved and prisms and other devices, simple surveyors' transits and theodolites were designed that really improved the state of the art well enough so that it became extremely accurate, and using those methods we were able to measure heights and distances to mountain ranges, for example. In the end, navigating by landmarks and then by the stars, using ships' methods of navigation, including the chronograph and the sextant and compass, navies were capable and explorers were capable of generating useful maps and records of their journeys. By comparing them with the known maps of the day, they were able to update those maps for greater accuracy. You see, this wasn't just about traveling around. Travel generally was for commerce. But warfare has always relied on good navigation, being able to find where your target is before you can attack. Warfare benefited greatly from the increased navigational skills and in many cases funded it. The development of many of these devices was paid for by armies and their research groups. One of the tools that made this navigation possible for weapons that had to be autonomous or move on their own was the gyroscope. Gyroscopes have some fascinating properties and have been in play for many long years. Galileo back in the 1500s and 1600s, and Christian Huygens in the 1600s, and Isaac Newton from the 1600s to 1700s used toy gyroscopes to understand many of their principles and made many interesting discoveries about them. The action of a gyroscope is similar in some ways to that of a compass, but it's a little bit different. With a compass, you're depending on the compass to point in a known direction, like true north, which is tied to the Earth's magnetic field. But a gyroscope can arbitrarily select a direction, be spun up in that direction, and then maintain it indefinitely. As long as a gyroscope is properly mounted and has a powered method of spinning so that it won't slow down, it will remember the direction it's supposed to point, in a manner of speaking. In the 1850s, a fellow by the name of Jean-Bernard Léon Foucault had proved that the gyroscope would maintain its rotational orientation even through the rotation of the Earth without disturbance. In the early 1900s, gyrocompasses were developed that actually helped navigate submarines, which made navigation in a submarine practical. Otto Schlick, who was also a German engineering inventor, in 1906, equipped a rapidly spinning rotor in a German torpedo boat, the Seabar. Normally the boat would roll by plus or minus 15 degrees in rough seas, but with his gyroscope in operation controlling the orientation, the roll was reduced to less than 1 degree total. Many of us have heard of Sperry Corporation. Well, in 1911, Elmer Ambrose Sperry, who was an inventor, was responsible for developing a gyrocompass that was installed in the U.S. battleship the Delaware. He'd also developed the first automatic pilot 2 years previously, which uses the gyroscope sense of direction to maintain the course of the airplane. In very short order, 3-frame gyroscope systems were developed that were used as the basis of navigation for almost every conceivable vehicle. The artificial horizon for airplanes is based on this principle as well. So the ability to automate navigation based on internal gyroscope controls became a fully developed art very early in the 20th century. German engineers rapidly came up with paired systems of 2 gyro and 3 gyro units that, when used in concert with each other, gave them the ability to create the V-1 flying bombs, the V-2 rockets, and the pilotless airplanes that they developed at the time. In other words, the basic elements of navigating in spacecraft were already in place by the late 1930s and early 1940s. But along with increased accuracy and better ideas of how to use these devices, we've also come to the point where, with advanced materials, we're able to make gyroscopes withstand incredible forces. The Copperhead tank killer missile, the one that is fired from a gun, typically has an impact of about 5,000 or 6,000 Gs when it's launched from the explosion that propels it. The gyroscope at its nose deviates from its upright position by less than 40 millionths of an inch under this shock, which is truly an amazing achievement. But not long ago, we also devised something known as the laser gyroscope, which uses a beam of laser light circulating in a frame, basically a series of hollow glass tubes, to measure the amount of spin or torque that's placed on it under any given circumstance. Further advances in something known as MEMS, or micro-electromechanical systems, has now devised gyroscopes and accelerometers, devices which can measure the amount of force that's being applied, and place them in tiny packages only 2 or 3 millimeters across. Typical devices today run about $5 to $10, and they contain 3 inertial movement systems and 3 gyroscopes in this tiny device. They usually only draw a couple of milliamps of current off a battery and can provide very accurate tracking. Every cell phone in the world basically has one at this point. But what about GPS, the one system we use and never really think about that much? What is GPS? GPS stands for Global Positioning System, and it was developed as a means of locating something accurately anywhere in the world. Initially, the Army developed it and worked on it to track packages, surveillance hardware, soldiers, locations of critical stuff that they had to know instantly. So how in the world does it work? Well, GPS is basically set up to work by time and distance. There are 24 GPS satellites functioning at any given moment. There are always at least 4 of them available for your receiver to detect. Each of them is sending a signal based on an atomic clock. Each satellite is synchronized with a specific known time code. Since it takes time, because of the speed of light, for the radio signal from the satellite to reach your receiver, the 4 satellites that you are detecting each send a signal that is supposedly from the same time code. By measuring the time of flight and doing a little geometric math, you're able to pinpoint where you're located with respect to those 4 satellites. Full-blown GPS units can be as small as a coin these days and can be applied anywhere, even put on something like a sticker. They can receive the information from the satellites and tell you exactly where they are located at the time. And this doesn't just include absolute position on the Earth, but also altitude, speed, and heading. So all sorts of navigation can be done with little more than some mathematics and a GPS receiver. But what about spacecraft? One of the most interesting types of navigating is moving through space. And in fact, there's a name for it as well. Instead of navigation, it's called astrogation. Now, technically speaking, if we followed the same structure of the word that astrogation and navigation would share, astrogation would literally mean traveling in a spaceship. We use the term as we use the term navigate, in fact. Navigating in space, or astrogation, is a little more complex than GPS or anything of that sort, and if you go too far from the Earth, GPS isn't going to work anyway, because you won't be able to get the signals properly. However, if we start with a known position of the sky, the stars, the sun, and the Earth, and we program a gyroscopic or inertial navigation unit properly, then we can use the sight of the stars as something to orient on, and the speed of travel, or acceleration, or time of journey, to determine pretty accurately where we're located. In these cases, we also have to take into account the gravitational field of bodies that we pass near, such as the Earth or the Moon, and even the pull of the Sun. So it becomes a rather complex task to astrogate. Here's an interesting fact. The original gold record on the Voyager spacecraft that left our solar system years before carries a pulsar map, a radio map showing our position in space relative to all of these radio pulsing stars that we've discovered. This is something that even aliens would be able to figure out if they ever intercept the golden disk on the spacecraft. After the break, we'll get into some of the specifics. I'm Sir Charles Schultz, and you're listening to Talk Universe. Now we're having some communication issues trying to hook up with our co-host Ed Minchow, and so I'm going to have to continue. I'll try again in a little bit, but I'll take some user questions and comments and do them on the air instead. And at least we have shared some of the material that he forwarded. We didn't have the sort of discussion I wanted. But we're going to continue, and we'll try reaching out again very shortly here. So Antoine from Louisiana says, what is the Southpointing Chariot? This is a great device that was invented many years ago by the Chinese. Now, apparently there were some earlier ones, but the best recorded ones and the ones with the most information on them are the Chinese Southpointing Chariot, which was a dead reckoning device, had a pair of wheels, and they worked apparently with some sort of differential mechanism. There are many different designs. You would set south, or the direction you wanted to point, manually at the start of the journey, and then as you pulled the chariot around, the differential mechanism out of the wheels would calculate how to keep that figure pointing south. And usually they'd have a carving of a hand or a dog or something on top that would point the direction for you. So they were said to first be built somewhere around the year 200 or so, and some of them were used up to about the year 1300. These were interesting dead reckoning devices that did use a sort of mechanical computation, like a differential device, to always point in the same direction, no matter how you turned it. Kaylee in Michigan says, my GPS doesn't seem to work very well in my vehicle. What can I do about that? You can get external antennas for a lot of GPS units and mount them outside the car. The real problem is metal blocks the signal, and many times if you have a windshield that has a coating in it, or on it, or some specialized light properties, the metal in the windshield actually can block the signal. It isn't pieces that you can see, so you need to get a clear, an antenna that's out in the clear so you can pick the signals up from satellites. Also be aware that it's certainly not going to work in a tunnel or anywhere like that. Now in a lot of cases, GPS units are programmed to go into what's known as dead reckoning mode if they lose a signal, and they'll continue to try and operate until they can catch the signal up again. Okay, Landrew12 writes, last year for Christmas, a friend gave me a box that he had made that would only open when I went to a certain location. Is this a GPS thing? Yes, Landrew, it certainly is. This is called geocaching. People, particularly hobbyists, will make boxes with a lock on them, and the lock will only operate when you reach the proper GPS coordinates. And I assume he gave you a puzzle or some sort of a thing to follow in order to get the box to open. Basically, there's a GPS receiver inside the box and a microprocessor. And when it sees that it's in the proper place, then it will activate the mechanism to unlock the box. That's a very interesting gift, and they were quite popular for a while. Also, keep in mind that if you're a clever programmer, you can make a device that will recognize when it is in successive locations, and when 3 or 4 or 5 locations have been reached, at that point it will do something. So this is a fun sort of thing to make, a geocache box. Stop and think about that for a minute. You could have a lot of fun with this. You could make a radio or an MP3 player for somebody as a gift, and then when they go to play it, it would only play certain songs in certain places. That would be a lot of fun. Colleen in Idaho writes, she's always had a fascination with gyroscopes and was wondering if they could be used for propulsion. Now, this is something that a lot of people have tried unsuccessfully. Gyroscopes have some fascinating properties, but they're not magical. There were a lot of people trying to make gyroscopes that would use precession to lift objects. Sometimes when you're lifting something that's gyroscopically active, spinning, it seems to be lighter, it seems to be easier to lift. And basically it's because it's changing the angle at which you're having to apply force in order to make it lift. It doesn't really make things lighter, but they certainly can make things do unusual things. Many years ago, some pranksters would put large gyroscopes in briefcases and hand them to people to carry around, and the gyroscope inside it would prevent them from turning the briefcase around the corner. It would want to travel in a straight line. Lots of laughs there. Arthur51 in Missouri writes, is it true that some animals can navigate magnetically? And is it also true that human beings can too? This is a question I've been asked a number of times, and thank you for the question, Arthur. Actually, yes. Some of the smallest animals, bacteria actually, have the ability to navigate by magnetic field. There's a thing called magnetotactic bacteria, and they have tiny nodules of magnetite, an iron oxide, Fe2O3, inside their bodies. And they become magnetized by the Earth's field, and so as they swim around, the tension created by the tiny crystals inside the bacteria exert a pull on the bacteria that make them align a certain way. They can actually home in on north, or they can head toward a magnetized object. So it's not unusual that there are simple organisms that can do it. More complex organisms definitely have the ability. Many birds do have tiny magnetic crystals in their nasal cavities or in cavities in their heads, and can use them to navigate by. Everybody's pretty familiar with pigeons navigating by the Earth's magnetic field, and that's how they do it. It's tiny crystals. They're called otoliths when they're in the ears, ear stones, and they have them in other cavities as well. So these tiny magnetic crystals inside their heads do exert a tiny force that their neurons can detect, and it allows them to home in on these fields. Human beings do seem to have some innate ability to sense a magnetic field. Some people much better at it than others. And it is said by some studies to be enhanced if you sleep in an east-west direction rather than a north-south direction. I don't know how reliable that information is, but it certainly wouldn't hurt to try. I know some people need all the help they can just to get from one room to the other. And incidentally, I'm going to take some time right now to make my book recommendation. And this is exactly in keeping with what we're talking about. The book is called Longitude, The True Story of a Lone Genius Who Solved the Greatest Scientific Problem of His Time. And this is John Harrison. He was a fellow who took up the naval challenge set up in the UK many years ago and developed the marine chronograph, an extremely accurate clock that allowed people to calculate exactly where they were. And his invention was, well, read the book. I think you'll find it's a fascinating story, and it's a look not so much at inventing as it is human psychology as well. And I think that if you read this, you'll find a lot of the issues that he faced still exist today in developing new technologies, unfortunately. So remember, the book is Longitude. It was published in 2007 by Davis Sobel, and it's a real deal, and it's a great story as well. Manny from Puerto Rico writes, does GPS work underwater? Actually, that depends on the type of antenna you have. I think that if you were trying to use it underwater, there'd be a couple of things you could do. One would be you'd come up to the surface every so often and verify your numbers, and you'd go down and navigate for a while. And the other is you could deploy a buoy that carries an antenna to the surface, if you don't mind dragging a buoy around when you're underwater. But it really is going to depend on the depth you're going to, and along with other factors. But yeah, in theory it could work as long as you could receive the signal. So yeah, I don't see any real obstacles to that. I have an anonymous question here, and it says, what was the first GPS satellite? That's easy. You can actually look that up probably right on the web. Navstar 1 was launched in 1978 in February, and it was the very first GPS satellite, and it was launched by the Air Force, the U.S. Air Force. They were going to put up a whole group, a constellation, as they call it, of satellites at that time. And it didn't actually become publicly available until the 1980s. Now, before that, there were other systems, and they were used at sea, and LORAN and LORAN-C were two of the methods that were used. They were a series of radio beacons, and you would pick them up and use a time differential method of getting around. So even before GPS, there were navigation systems that generally would work on the ocean. The LORAN system was one of them. Now, here's another thing. GPS typically has a best resolution of about a meter or so. And that's not very good for some things. And what a lot of people have done is they will put a local broadcast station that sends out a timing signal, and they'll combine that with GPS data, and they can get signals that will bring them to within a centimeter or so of their target that way. This is used a lot of times in robotics and research projects where precise navigation is necessary. Of course, these days, robotic intelligence is getting to the point where they can sense where they are using other methods very accurately. But a combination of GPS and a local radio transmitter can give you extremely fine precision of position, which is going to way outweigh the sort of resolution you get on GPS signals as a whole. I'm still having communication issues here, so I think we're going to not be able to have Ed Minshaw on the show this time around. We're definitely going to get him in on another show very shortly here. And I'm going to continue and do a few more user questions. Parker23 in Wichita says, how did the North Star get to be the North Star? Well, that's just actually a matter of chance. You know, the Earth's pole wobbles slightly as it spins. It's like a big gyroscope, and it precesses. It's not exact. It's always slightly wobbling. And because of this, it aims at different points of the sky. We can look at old archaeology sites, and we can see how they line up to the stars in times past, and they don't line up that way today. So we know that the Earth's pole was pointed differently then, and it matches up to the estimated dates. But the North Star, Polaris is what it's called, is actually only about a degree off of true north. It's not really at true north. And it's because it's just a random star that happens to be fairly bright and happens to be in the right place. Over time, the North Star has changed because of this wobble of the Earth's pole. But right now, it's in a pretty good position. Remember, it's not exact. It's a little less than a degree off of true north. But it's close enough that you know that you're looking at north. So it just happened to be in the right place, and that's the name of that one. Here's another funny thought. In the south part of the sky, there isn't a North Star or a South Star. There isn't an equivalent. There is a bright star, a fairly bright star, Sigma Octans, which is a degree away from the south celestial pole. So, you know, it's not quite as close as Polaris, but it will function well enough if you know how to find it. After all, you know, it's just another star in another sky. Dave from Raycross says, how many GPS receivers are there in the world? Wow, that's a tough one. All I could say is billions. You know, there are so many hundreds of millions of cell phones, literally billions of cell phones right now, and many of the older models had GPS in them, and all of the new ones have GPS. And there are so many just Garmin and other navigating products. I really don't know if there's an easy way to estimate that. I suppose we'd have to call the microchip factories and the companies and see how many units they shipped. Wow. I would just have to say, probably, if I were asked to give an answer, and that's what you've done, I'd say there probably are about 20 billion or more functional GPS units in the world right now, just off the cuff. And that wouldn't surprise me if that answer were correct. That's a lot of navigating. Barry in Minnesota, here we are. Yes. Barry in Minnesota says, I have an electronic compass and it doesn't have a bar or a magnet in it. How does that operate? Okay, Barry, this is a device that's called a flux gate magnetometer, and it works by generating a weak magnetic field in a piece of ferrite, generally in the shape of a ring or a donut. And what it does is it writes a pulse of magnetism into the ring, and then it reads back the energy it takes to change the polarity of the ring. Now, it typically has two coils at right angles, like a cross or an X across the ring. And if you move it around, if you rotate the ring in the Earth's magnetic field, the Earth's field will slightly influence how much energy it takes to read and write that magnetic signal in the ring. And so you can determine from the two coils just how the ring is rotated. So it does in fact measure where true north is, or magnetic north, I should say. But it does so by writing a weak magnetic field in the ring and then erasing it again and seeing how much power it took to do it, the threshold at which it changes. So that's the flux gate magnetometer, a really simple and clever device, and it makes a great compass. It doesn't have real high resolution in most cases, but it's significant enough to get that little display under your mirror in your car saying north or west or east. So we're down to the end of another show, and it's been a good show. I'm really not too pleased that we were not able to get Ed on. He's always a great person to talk with, has a lot of good information. But we will have him on in a future show, and I think that we've covered a lot of points about navigation, and as usual, if you have questions, email them to me or send them to us on Facebook. talkuniverse.org is our website. And remember, we have everything we need to create everything we'll ever need, and make the world a more beautiful place for having lived in it. I'm your host, Sir Charles Schultz. This is Talk Universe. Have a great evening. Good night.